G'day. Well, if you've been following my video series, you will feel, I trust, very competent at using the chain rule, the product rule and the quotient rule to find derivatives of functions. Now what you've been finding the derivative of are what we call explicit functions. Things like this: y equals x squared plus 2x minus 3, y equals cosine of 3x plus 1 minus x squared, y equals 4 over x plus x to the 7. Situation where y is on one side of the equation and everything on the other side of the equation contains an x or a constant. There are no y's here and there are no x's here. This is what we call an explicit function, where y is very explicitly written as a function of x. Now what we're going to look at in this video are what we call implicit functions. Now there's nothing particularly complicated about them, well, not in concept anyway. All that an implicit function is something like this. If we take the explicit function y equals 2x plus 3 and we rearrange it to write y minus 2x minus 3 is 0, we now have an implicit function. The relationship between x and y is implied in that statement, but it's not explicit. It only becomes explicit when you rearrange it. And the traditional definition is that you have some function in terms of x and y equal to 0, creating an implicit relationship between x and y. Now, a few little comments. First of all, these aren't always functions. Some of the graphs we get create relations. I hope you remember the difference between a function and a relation. A function is something very predictable. Mathematicians like predictability and definiteness. Now, if I choose an x value and there is one corresponding y value, and I choose some other x value and there's one particular y value, and some other x value and there's one particular y value, and in fact everywhere I look there is just one value on the graph for every x value, this is what we call a function. And traditionally we talk about a vertical line test. If you graph it and you draw a vertical line anywhere on the graph, it will only cut the graph or intersect the graph at one point. This makes it very, very clear. Now a relation, I should put here function. A relation, short I guess for a relationship between x and y, could be anything. You can have the most amazing curls or what we call cusps, lines curving back on themselves, loops, all sorts of things, where if you choose a particular x value, there may be multiple possibilities for y, and this is confusing. Now, at school, the simplest relation you study is a circle. And you can see, first of all, it does not pass the vertical line test. If you draw a vertical line here, let's say this is x equals 5 and here's x equals 3, you can see there are two positions on the circle where we have some y value, that one and that one. Now it's not terribly confusing, but it's more confusing than a function is. Now why do I explain all of that? Well, when we have some relationship between x and y, although we call them explicit functions, they're not always, they're explicit relationships. And I could, if I wanted, rewrite this in another way. Y equals, or y minus 2x equals 3, for example. Now, strictly speaking, it's not some function of x and y equal to 0. It's not far off it. But x and y are still implicitly related. Now, some clarification. These are explicit functions. explicit. They're implicit. Technically that's not according to this definition, the pure definition if you like, but we include all of these as explicit functions, as implicit functions, or implicit relations, more precisely, when we find their derivatives. Now we can in fact find the derivative of relations or functions like this more easily than we can an explicit function, because sometimes the relation is rather difficult. I want to show you a couple of examples, and we'll build up in difficulty over 3 or 4 quick examples in this video so you get an understanding of what we mean by finding the derivative implicitly. Now, if I had the explicit function y equals 2x minus 3, or plus 3 I think was what I had, really doesn't matter that much, and I find the derivative, I would write dy dx, because I'm finding the derivative with respect to x, or if I'm being a little bit lazy, y dash equals, and the derivative of 2x is 2, and the derivative of a constant is 0. So there's my result. Now, this is explicit. If I rearrange this to get y minus 2x minus 3 equals 0, I now have an implicit function. And what I'm going to do is I'm going to find the derivative with respect to x of everything in the equation. Now, the derivative y with respect to x is dy dx, which I will write as y dash. The derivative of negative 2x or minus 2x with respect to x is the number negative 2. The derivative of the constant negative 3 with respect to x is 0, and the derivative of 0 with respect to x is 0. And if I rearrange this, I get the same result. Now, it was really the same equation, the same graph, the same function, and of course I would expect the same result. But this is how the derivative is found implicitly. Now, before we look at harder examples, because I think you will agree that's quite simple, before we look at harder examples, I want to explain a principle. The principle is this. If I have some function of x, and I find the derivative with respect to x, I will get 4x cubed, in this case. That deals with the power. For those of you who've seen my chain rule video, I hope you'll understand what I'm doing here. And if you haven't seen it, let me encourage you to do so. I think I'll create a link for you. But we deal with the power of 4 first, and the 4 comes down, we drop this by 1. And then we find the derivative of x with respect to x, which is 1. And strictly speaking, we should have times 1. No one ever bothers, because that's just the nature of taking the derivative with respect to x. However, if I had something like y to the power 4, and I took the derivative with respect to x, not y, I would get this. First I would take the derivative of the power, and I would get this. And then, being the chain rule, I would then take the derivative of this expression inside the power, or under the power, which is y, and I'd take the derivative of that with respect to x, which is dy dx. I will write it this way, which of course we could write as 4y cubed times y dash. Now I've got to be careful, I'll put it on a little bit of a slope there. It's not meant to be a power 1. So you must be very careful when you write them. Basically, any expression that has y in, when you're finding the derivative with respect to x, will have a y dash at the end. For example, cos of 4y rather, the derivative with respect to x will be, the derivative cosine is negative sine, times, the derivative 4y is 4, times, and then the function inside that is y, and the derivative of y with respect to x is y dash. There is always a y dash at the end when you're taking the derivative of any function of y with respect to x. That's the thing to watch for. There is never a y dash cubed or squared or anything weird, it's just y dash. And the beauty of this is, no matter how complicated your original implicit function or implicit relation, when you find the derivative, you'll have at least one y dash, maybe 2, 3, 4, but they'll just be y dashes. So effectively you have a linear equation with y dashes, or dy dx, and it's quite easy to rearrange the equation to find the derivative. Very clever technique. So let's now apply it to some examples. Well, the first example we're going to show you, we're going to discuss, is this one. Let's create a circle of radius 5. Why do we do this? This is traditionally done first in textbooks, and for a very good reason. One, it's relatively simple, and two, it's a relation, and it's the only relation that you really study in junior high school, certainly here in Australia. Well, let's find the derivative of this with respect to x. The derivative of x squared is simply 2x, you know that. The derivative of y squared, now beware, it's a function of y, and we're taking the derivative with respect to x. So the derivative of y squared is 2y times, because we've taken the derivative with respect to that power, times the derivative of the function inside, which I'm going to write as y dash. You'll find that mathematicians tend to prefer, when they're taking implicit derivatives, to use y dash, because dy dx all the time becomes a bit tedious. But just be very careful of that power, of that symbol up here in the superscript. It's not a 1, it's a dash. In fact, as a little aside, when you find derivatives, if that's your original function, and you start finding derivatives, they're y dash, y double dash, y triple dash, and y, not sure. A lot of textbooks don't show this, but it's actually this. And your fifth derivative and your sixth derivative. Yes, they're Roman numerals. So many textbooks don't explain it. But even though it's y1 Roman numerals, we call it y dash. Anyway, that's a little bit of interesting information. Let's keep going. The derivative of 25 with respect to x is 0. So now we have an equation that has a y dash in it. And we want y dash left on this side. Now the first thing I notice is we have a coefficient of 2 in common, so we'll divide everything by 2. I'll move the x onto the other side. And I'll divide by y. Now, let's stop for a moment. When we find an explicit derivative, we only have x's over here, not an x and a y. So this is a little bit different. What I'm going to do is stop for a moment. I'll have to eliminate this from the board. I'm going to stop for a moment and show you what happens if we try to do this explicitly. And we'll see how useful this might be and why this implicit derivative can be very, very useful. But let's have a close look. Well, let's first of all create our explicit function. And now I want y equals, so I'm going to take this original equation here and rearrange it to look like this. That's easy enough. Then I'm going to take the square root of both sides. Now, this is something that's not very well done in school textbooks, largely because students in junior high school are not introduced to the idea of absolute values early. And I was taught the traditional way, without the absolute values, the incorrect way if you like. And I had a major external exam once, and the only mistake I made in the exam was this, saying that if x squared equals 4, then x equals 2. And I neglected to write plus or minus 2. And it's bugged me ever since. Now, when you take the square root of both sides, this symbol means the positive square root. And the positive square root of y squared should be written as the absolute value of y. And then the next step is to remove the absolute value signs and write plus or minus y, or in this case we can put it over here. And that is our explicit function, or relation in this case, because we're accepting positive and negative values. You can see that for any value of x that I place in here, that's not equal to 5 or negative 5, any value of x in here less than between negative 5 and 5 is going to give me a value here which is positive or negative, so I get two values for y. Well, of course we expect that for a circle, don't we? If that's negative 5 and that's 5, any of the x values in here, like x equals 1, I expect to give me two values on the graph. So it's not a function, it's a relation. Now let's find the derivative. I'm going to first of all write this as plus or minus 25 minus x squared to the half. Now the derivative is going to be chain rule. First deal with this power. Plus or minus half 25 minus x squared to the negative half. That's dealt with the power. Times the derivative of what's inside, well the derivative of 25 is 0, and the derivative of this is negative 2x. Let's try and tidy this up a bit, shall we? The negative multiplying the positive plus or minus gives us a minus plus. That's a relatively trivial little thing. We won't deal with that much at this point. A half of 2x is simply x. And the power of a negative a half means that we've got this on the bottom. Now please notice I suppose I should have left the negative separate from this. You'll suddenly understand why. What have we got? I'm going to shift the positive and negative down here. I have negative x, and what is plus or minus the square root of 25 minus x squared? It is y. It's the same thing. Now, because y is equal to that, we often leave it this way. In fact, we always leave it this way when we find the derivative explicitly. But I think you agree that's a lot harder than doing this. Now, what happens if we have a particular point? Well, since I chose 5, we know that the 3, 4, 5 triangle is a right angle triangle. So let's imagine I go across to the point 4. I'm doing I didn't intend this to be quite so small. But across 4 and up 3. So this is the point 4, 3. And if I go across 4 and down 3, I get the point 4, negative 3. And you can see that for the same x value of 4, I have two y values of plus or minus 3. Well, using this, rather than this complicated one here, if I wanted the gradient of the tangent to the circle at this point, I would substitute x equals 4 and y equals 3, and I would get a gradient of negative 4 on 3. And you can see here it's a negative gradient, and it's pretty close to negative 1, the gradient. Pretty close to a 45-degree angle. What if I wanted, I should put here at 4, 3. What if I wanted the gradient of the tangent here at the point 4, negative 3? Well, I would substitute x equals 4 and y equals negative 3, and I would get y dash equals negative, now x equals 4 and y equals negative 3, and that would equal, I'm running out of board so I'll go across, that would equal 4 plus 4 on 3 at 4, negative 3. And you can see that the gradient is in fact roughly plus 1, it's roughly a 45-degree angle there. So in fact, not only do implicit functions allow us to find the derivative in terms of x and y with slightly more complicated equations, but it means that if we know the location of the point that we want the gradient at, we can substitute and find it relatively quickly. And we can do it with relations as well as functions. Very, very clever. So there it is. You've come a fair way with me in probably 10 or 15 minutes. I'm going to ask you to bear with me for one more example, and then I'm going to create some other videos of more complex examples. But let's do one more slightly simple one. We'll do something that you almost certainly will not have seen in high school. Here's one that would be quite fiddly to do explicitly. X to the 2/3 plus y to the 2/3 equals, let's say, 4 to the 2/3. Now, this kind of graph produces what's called an asteroid, not asteroid, as in the lumps of rock circling the sun between the orbits of Mars and Jupiter mainly, but an asteroid. And the graph of an asteroid looks like this. You can see that if y is worth 0, and I just ignore the powers of 2/3 because x to the 2/3 equals 4 to the 2/3, you can see that x would equal 4. It turns out that x could also equal negative 4. Because although you've got a cube root, you're squaring, which would get rid of the negative sign. Again, if x is 0, y would equal plus or minus 4. So what makes this different from a circle? Well, interestingly, these powers make the curve do this. There you go. We have an asteroid. Now, you won't have seen this in school. You can see straight away that it does not pass that vertical line test. It is not a function. But we're going to find the derivative implicitly. So let's find the derivative. The derivative of this is 2/3 x to the negative 1/3. That deals with that power. And of course we're taking the derivative with respect to x, and dx is 1, so multiplying by 1 we don't normally bother with. Plus, let's do it here. Deal with the power times, and now we have to multiply by the derivative of y with respect to x, which is the y dash. Remember that. And the derivative of this with respect to x is 0, because as complicated as it looks, it's just a number, it's a constant. So there we go. This is traditional. We've done that many, many times explicitly. And this one, we treat the same way, but because y is a function of x, we still need that derivative with respect to x. Now, multiplying through by 3/2, or dividing by 2/3, will give us this. Subtracting this from both sides would give us dividing by this would give us this. sorry, that's a negative third. I knew something was going wrong there. And I'll do it this way. There are a few ways of looking at this. Because they're both to the power of a negative third, I'll do that. And because it's a negative index, it means I can invert the fraction. Or I can write it as the cube root of y over x. Now it does have a cube root in it, but it's not that complicated for a rather weird looking equation. Now if we knew the location of some point somewhere on here, and we wanted to know the gradient at that point, we would substitute the x and the y value for that point, and we would find the gradient. And there it is. So what do we know? Explicit functions would have the form y equals some function of x. That's explicit. An implicit function traditionally has all the x's and y's on one side, but when we're taking the derivative implicitly, we will handle anything with x's and y's on either side or both sides of the equation, and constants as well, like this. And implicit differentiation, the thing to watch out for is when you're differentiating a function with a y, you'll get a y dash at the end of that expression. And that will come out in the end as the derivative. And it's a profoundly useful tool. Now, not everyone thinks the same way I do, and there are other videos on YouTube that explain implicit differentiation. If you've enjoyed this one and it's made sense to you, then please let me know via the comments. If you found other videos that explain it better, then please use them. I don't pretend to believe that I've got the best answer or the best solution or the best explanation for everyone on the planet, because we all think differently. But if you've liked this, then please like the video. Please subscribe if you'd like to see more and find out what I'm producing. And please watch out for the next 2 or 3 videos, because I'm going to produce some slightly more difficult examples, or at least solve them. They'll be much shorter videos because I'll just have one example per video. Thank you very much for watching, and I look forward to seeing you again.